probably get started. So welcome to the Robotics Colloquium. Today we have the pleasure of having Coline visit us from Google Deepmind. Coline is a senior research scientist. She received her PhD from Berkeley, advised by lots of people, and has won the NSF Graduate Fellowship, published a lot. And what I find particularly compelling about Coline's work is that she operates under real-world assumptions without taking shortcuts, like I like to do. And I think she's done some really fantastic work at DeepMind on scaling, showing generalization. And yeah, I'll let Coline take it away. But yeah, it's really a pleasure to have her here.
Thank you very much for inviting me to speak here today. As Abhishek said, I'm Coline, research scientist at Google DeepMind. Some people wonder where I am now. I am now in California, but I was in London for 3 years, and this work was done mostly with the folks in the London side of the Google DeepMind unit. And so today I'll be discussing this work that we did on RoboCat, a self-improving agent for robotic manipulation. Despite the name, this has nothing to do with cats. The name is derived from the work on gato, which means cat in Spanish. So a lot of people apparently did not make this connection, which in retrospect, we should have predicted. But that is the origin of the name. There is no chasing yarn or balls or mice or anything like that.
So what did gato have to do with cats then?
Gato is an acronym for like generalist agent something. So this was a large piece of work that was contributed to by a lot of people of the robotics team and many collaborators, an intern who was with us last summer, Agam Gupta. And without all these people, this kind of scale of work would not have been possible. So I really appreciate that we were all able to work together on this project. And so a brief and very incomplete history of how we got here is a lot of us were working on robotic manipulation for a while, but we had been mostly focused on solutions for single task agents. And I had dabbled a bit into multitask setting in grad school, and I often failed to show any positive transfer across tasks. Like if you have 5 tasks and you train on them, that's usually not better than training on each of the 5 independently. So we were kind of sad about the state of multitask robotics. And when transformers came out in 2017, this kind of transformed the landscape of language learning and then later vision, and a lot on the kind of generalist multitask front of the learning problems. And these developments led to progress in multimodal behavior modeling. So this is the generalist transformer agent Gato shown here, which was able to play Atari, caption images, chat, and show some robotic manipulation capabilities. And at the same time in robotics, recent works from the kind of Google Brain side of the robotics team had focused on bridging the gap between large pre-trained language models and vision-based manipulation by training language condition transformer-based policies to solve visually diverse tasks. This is like the RT1, PALMI, RT2. And this was kind of the landscape that we were working on RoboCat in. So what we were interested in doing here is how to lower the cost of acquisition of new robotic skills. And we were kind of thinking of how could we get a foundation model for robotics that could be a multi-embodiment agent capable of solving a large set of precise and dexterous tasks that could be trained on broad robotic experience that comes from different sources of data. So we were kind of imagining this grand goal. And we were thinking if something were a foundation agent, it should be able to quickly adapt via fine-tuning to a broad set of new downstream tasks. And we'd like it to be able to self-improve, to get better by practicing the new tasks that it's learning, collecting more experience autonomously, and continuing to train. Because being dependent on pre-collected expert demonstration data is quite limiting in terms of the set of tasks that we can do. So I don't know if I'm going to make any claims about achieving a foundation model in this talk, but we like to think we're moving in that direction. And so we propose RoboCat as a self-improving agent for robotics. We trained RoboCat on a very large set of vision-based tasks from a variety of embodiments that differ in degrees of freedom, observation space, action space, and control frequencies. Our agent is able to be adaptive via fine-tuning to new tasks and embodiments. We use the fine-tuned models to collect additional data on these new tasks that it has learned, and then we take this data, add it back to their pool to train the next generalist agent that can now perform a larger set of tasks. So this model is based off of Gato, as I mentioned, which the idea of Gato was like we should be able to train behavior models the same way that we train language models. Just everything gets tokenized in, and we output tokens out. And we can mix things of different modalities together because they're all tokens, and so they all go into a big context, and it just, tokens go in, and you have to predict the right token out. So the architecture we use is very similar, except that we use a pre-trained visual encoder on the images instead of learning that end-to-end because it allowed us much faster iteration since we didn't have to train that every time. And so here, our inputs are the images and proprioception coming from the robot, so the images are tokenized with a VQVAE. The proprio is just discretized into buckets. And the actions that come out are just discretized binning of the action dimensions. And those get used to control the end effector of the robot.
Quick question.
Yeah.
Does the VQ matter, versus something continuous? Does the discreteness of the representation matter, or?
So the alternative we compare to is what's using Gato, which is that you take the image, cut into patches, and then encode those into embedding space.
With contrastive learning or end-to-end?
No, just end-to-end. And that also works well. It takes twice as long to train the model.
If there's a different pre-training method, what I'm trying to say is, does discreteness matter, or does it just some pre-training? Or does the particular pre-training matter?
I think if you want to put it into this, you need something in the right space. So either you want to train the embeddings with it or tokenize it. Yeah. I think it's pretty flexible. I don't think it really matters. I think we could have done something better than what we did do, which is just what we kind of had. And for the pre-trained encoder, we needed this to be pre-trained on a broad set of images. So we have ImageNet in there to make sure it was general enough to take into account the new tasks that we haven't seen yet. Also, this is the way we tell the agent what tasks to do is that we provide a goal image. Though I will clarify that we're not doing goal matching, so it doesn't have to produce the exact same behavior as in the goal image. The goal image is an image of the task that we want being successfully done. So here, if we have an image of this stack, then that means the task is to stack the green on top of the red and the blue on top of the green. It doesn't matter that they're in this exact position. And then another note with this model is that we can, because it's just tokens in, tokens out, it doesn't, we can do natively multi-embodiment because we're not limited to a certain type of action prediction, and we're not limited in terms of size of the input prediction. So some of our tasks, some of our embodiments have more proprioceptive inputs. That's just more tokens going in. And some of them have more actions. That's just more tokens coming out. So we don't do any sort of matching to make them all have the same 6 dimensions. And so just as an example of how this works once it's trained, if you provide a goal image to the agent, like here, the task is to put the large gear insert the large gear. Then the model is conditioned on this image, and we'll pick the large gear up and put it into the peg. So how do we train this model? So as I mentioned, we kind of think of this as a cycle, but we have to start the cycle off somewhere. So we start the cycle by training a multitask, multi-embodiment visual goal condition model. And we need a large data set in order to actually bootstrap to get something that can generalize to new things. So our initial data set for the first iteration is mostly simulated data. We had this prior work on stacking that was focused on stacking red object onto blue object. So we have a bunch of real-world data of just red onto blue that we had collected previously on a 5DOF Sawyer. So we have this data, so we should use it. So we add it to the data set. And then we also have a bunch of simulated data of different tasks with these objects and with these gears. And the sim data is collected by training an RL agent from state to solve these tasks. And then we just roll it out and get the images from the episodes. And then to do the goal conditioning, we take if it's a successful episode, we can take either the last image from that episode or the last image from another episode performing the same task. And those are valid goals to provide to the agent during training to condition for the trajectory. And if it's a failed episode, we can only take the last image of that trajectory because it's failure, but it's successfully achieved its final state. So we can do this hindsight relabeling. And the data that we're having here, we have two simulated embodiments, a 7DOF Panda arm, panda, 7DOF Sawyer, and then this real-world 5DOF Sawyer arm on those red on blue stacking. And this will come back later, but for this initial iteration, we held out some of the task object embodiment combinations to study generalization. So we have a model that can perform a variety of tasks, and most of them are in simulation. So we want to take this agent and fine-tune it to a new task. So we have our teleoperators in the real world, and we have them collect 500 demonstrations of a new task, and we want to fine-tune RoboCat to that task. So we look at a couple different tasks to fine-tune to. We have, again, our RGB objects, we call them, that have different shapes, and we can get this. I think we have an inverse pyramid and a tower, 3 objects stacked together. So we have teleoperators collecting these, and then we also have these fruit from the YCB data set where the task is to lift them, and turns out the fruit also have vegetables that are matching, so we have vegetables, and we have these 2 real embodiments. And some of our data was at 10 hertz and some of it was at 20 hertz because of technical issues, but we just threw all the data in. Why not? So we fine-tuned, and now we take our fine-tuned agents and we just deploy them in the real world because we have models, they should be able to collect data. So we collect data from our fine-tuned agents. The successes are a bit low because we kind of did multiple attempts at this. So whenever we took an agent and fine-tuned it, we evaluated it, and we always kept all our evaluation data. So even the agents that weren't very good, we still evaluated them. That's 100 episodes, that we shouldn't throw that away. So we kept all of the data that we always generated and got data for these different tasks. And for example, for these cuboid type objects, we have automatic resets already implemented from a previous paper that just kind of located the blobs and regularly reshuffled them. For the fruit and vegetables, we did evaluations by mixing the different policies. So we had like a policy fine-tuned to lifting banana and a policy fine-tuned to lifting apple. And we kind of evaluated those interleaved so that they would mix each other up. So this was a way to get really like autonomous data collection where we didn't have to have someone sitting there and just mixing the objects up regularly. We also, at the same time, combined with another project that was working on learning success and reward functions from data. So here we have the data was being sent to raters to like kind of mark when an episode is successful, and then automatically sent to train reward functions for each task. And so then we could just use these automatic success labels. They're not always 100% accurate, but they allow us to like pretty easily sort the data into like this, these 20% are probably failures, these 80% are probably successes, and we use those learned success failure levels for deciding on the goal sampling that I mentioned earlier when we train later. So this is like a kind of fully autonomous setup for fine-tuning a policy, deploying it in the real world, getting labels, and adding it back to the data set. Yeah.
Can you go back? When you visualize this data, is it exploratory in a meaningful way? Is it just kind of random? What's the vibe of the data?
It's not really exploratory. It's just it just fine-tuned via BC on these teleoperated labels.
Collecting exploratory data, which should be not there should be some diversity in it. Right? So how diverse is the data?
I'm not sure it's really trying to be diverse. We really did nothing. We literally took the fine-tune agents and put them in. What it does do is it gets visual diversity because the teleop data, maybe we only have 100 or 500. So there's a lot of initial states not represented. But since it's fine-tuned to specialize the that task, it's kind of robust to those. But then when we put it back into the generalist, that visual diversity from automatically collecting 10,000 more episodes helps quite a bit. But I think you're totally right that it would be much better if this was being smart.
Yeah.
But it's not. But that's a great area for improvement. What else was I going to say? The other thing is that this is from a variety of agents. As I mentioned, we did multiple attempts at fine-tuning and evaluation. So we do get some diversity in that some of these are earlier in training, some of these are later in training, and things like that. OK, so we collected more data and more tasks. So we should just train again. So we train iteration 2. So in iteration 2, we have quite a bit more data because we have all the old data. And then at the same time, we were collecting teleoperation data for this gear insertion setup in real and in simulation. And then we have our additional few-shot demo and self-generated data. So we now have 4 embodiments and 240 tasks. So we train our new generalist on all of this. And this is a lot more real-world data than in the first iteration. So if we just take a look at this agent, then we can evaluate it again on the real-world task. And by the way, you're not supposed to put your hand into the robot bin while it's running, so don't do this at home. I like there how it's hesitating, wondering if it should put it on the red or the green. And then we can dive a little deeper into the results. So this is maybe a bit hard to read, but in the top half, we have our sim tasks. And the sim, basically, some tasks are a lot harder than others. Unsurprisingly, stacking one object is a lot easier than stacking 2 objects on top of each other. But we do see that generally, if we have enough data for a task, we can get the agent to be pretty good at it. In the real world, our tasks are the self-improvement. So this is data where we only had, I think here we're using the 500 demonstrations and the whatever self-improvement data we have for those in the curly brace. And then at the bottom, we have these NIST gears going on pegs, where we had a lot of teleop data. So those were accomplished quite well. And we see that, oh yeah, and then here's this task is super hard. This is the inverted pyramid. We tried to get sim data for this task, but we couldn't get a reward function that could be learned in sim. So we were unable to get sim data, so we only have real data. And we were able to get, 17% success on it from 500 demos. And so I want to note that also when there's a task that we have both in sim and real, we made no effort to match these environments. Like, this is not a sim to real alignment setup. We don't use any visual randomization, and we didn't do any sys-ID. Like, for example, the pegboard here is green, and then the real world is gray. Why did we do that? I don't know. But it does make it more difficult to transfer. We really kind of just were like taking all the projects that were generating data and throwing it into this, and then evaluating it without thinking any further. Yes?
One question, do you have a sense for example, with this goal specification for the image, how it would transfer if you, whatever, now you want to stack soda cans or books or something like that, real world,
yeah,
natural objects?
Yeah. I don't have that video in here, but we did do some like just random attempts of like seeing what we could do. If the manipulation problem is easy, it can do it. So like, I think it's a lot by color. Like if you have a red soda can and like a green bowl, and you give an image of that, it will do it if it can pick those up. If they're hard to pick up, then it has to learn on those objects.
It's usually more subtle than red or green, then it's also going to be harder.
Yeah, probably.
So, okay.
I think what we've found here is like if you have the data, it can work. And then if you wanted something where you don't have the data, then you have to do something a bit different. Oh yeah, but so that's it. So we can throw data at RoboCat, and it will learn the task if there's enough data and solve the training tasks. Some people might ask if you really need this to be like a robotics agent. A popular alternative could be to take an off-the-shelf pre-trained vision model and then fine-tune that. Like whenever you have a robotics test you need, you would just fine-tune it to that task. This was an approach that some people were working on in our group, and that seemed to work pretty well. So we compare RoboCat with these high-capacity pre-trained visual models that we fine-tuned to each task independently. We tried a really large number of these and picked the best two to compare to, which were like using NFNet pre-trained on clip, fine-tuned at the 6th layer forward, or like SWIN, also fine-tuned on clip, or pre-trained on clip. We have a huge table of these in the appendix, but these ones were consistently the best. So if we look at sim tasks, it's not bad at the stacking tasks to do this approach. But then when you get into the harder sim tasks, it's a lot worse than RoboCat. That actually learned on robotics data. The real world, you might think, okay, these are pre-trained on real images, so maybe they do better in the real world data. But here we have much less episodes to fine-tune to. So they actually are a lot worse. So there's one task where the visual model is better than RoboCat at learning the real task, which is the tower building. But other than that, the model that actually did see a lot of robotics data, I mean, you might say this is not surprising, but we had a lot of people that argued that this would be a better approach. So we wanted to actually verify and check that our robotics data is useful at learning new robotics tasks. And then we want to see how this fine-tunes to even new tasks. So we had iteration 2, and now we want to fine-tune it again to new tasks. So we look at tasks where we have the same object that comes again. So here we have to remove and insert fruit from the bowl. Well, we already saw this fruit in the fruit lifting task. And then we have a completely new set of objects to insert and remove these shapes from the shape cube. Here, I think we're a little limited from the vision encoder at actually locating which hole to put the object into, because it has to put into the right hole and then oriented correctly. So I think this is where our like VQGAN approach might be limiting us quite a bit. Because the VQGAN never saw these objects. But we're able to remove the cubes fine. So the manipulation side is OK. And then we also fine-tuned to a completely new embodiment that has twice as many degrees of freedom to control. Here we have this like in-house made 3-fingered hand on a kuka. And we train it to lift the gear. And so here, since our method is like this tokens in, tokens out, the agent just has to learn to output 14 tokens per action instead of 7. And it's able to do that from 1,000 demos. And so again, with these fine-tuning tasks, we compare with those vision model baselines. In this case, there's only like 500 to 1,000, or actually 100 to 1,000, yeah, 500 to 1,000 demos to fine-tune to. And so here we really see the benefit of having trained on all that previous robotics experience on learning these new tasks. The low data regime, those pre-trained vision models are just not very good at picking up this manipulation behavior. So we can look at another video of the fruit insertion. Here, I have to press play. So here we're just running, goal image. The lemon is out of the bowl. We're not checking that the goal image has like all the other fruit in the bowl. So the goal image is like, there's just like the lemon is out of the bowl, so it takes the lemon out of the bowl, or the strawberry is out of the bowl, so it takes the strawberry out of the bowl. And then we can just run this policy 3 times to empty the bowl, or 3 times to fill the bowl. So I fine-tuned to this bowl, but I hadn't seen it before the fine-tuning.
If you switch out the bowl, like how often do you have to fine-tune?
Well, I fine-tuned to this insertion removal task.
But like, let's say I switched out.
Yeah. If you, I don't know. I'd be curious. Yeah.
It's like let's keep swapping out. Then
Yeah.
At some point it should amortize, right? Like,
Yeah. Exactly. Cool. So. Speaking of generalization, so we had this, as I mentioned in iteration 1, we kind of held out a number of the tasks to check for generalization later and adaptation. So we have this, like, we call this iteration 1 RoboCat lim because it was trained on limited data. And some things we wanted to look at is how well it generalizes to a perceptual variation of a task. So this is like stacking. We held out the blue on green condition. So it saw blue on red and green on blue, et cetera, but not blue on green. Our cuboid things, there's like, this is from previous work, so it's kind of, I don't know if I want to explain everything, but basically we have these triplets that are 3 objects with shapes, and each of them has a different shape that kind of looks for a different affordance. And so we held out one of these triplets from our data. We also compared fine-tuning to teleoperated data versus expert agent data. We wanted to see how well our model performed on real versions of the sim tasks that we're seeing during training. Completely new task family or behavior, and then an unseen robot. So if we walk through this, so here's our blue on green for the Sawyer robot. We have 0 episodes, 100 episodes, 500, 1,000. So we can see that this one did not generalize 0 shot to this new visual perception, but it did learn very fast once we gave it 100 demos. But on the other hand, for some reason, the Panda, so the Sawyer and Sim had only stacking, so it had only stacking of the non-blue and green data. The Panda, it had stacking of non-blue and green, but it also had the tower building and pyramid building tasks in it. So it's a lot more other data, so it was able to adapt to, it was able to 0 shot learn the blue and green much better. So this like shows that more data I have, the better you generalize to the missing data. For the held out object set, for some reason, it kind of doesn't improve with more data. It may be in part because it's not noticing that it's different objects from the shape in the images. I'm not sure. Here in the real world, we did fine tuning to the real world blue and green stacking, where we had a data set of demos from a human teleoperator versus rollouts of an agent that was good at stacking these objects. So we tried both fine tuning to see if there was a difference. Interestingly, like I thought the agent data would be easier to learn from, but it turns out the demo data gave better results. If we look at a fully new, a task that we saw in sim but didn't see in real, it's quite a bit better than seeing a new task that we didn't see in sim at all. Though there's no zero-shot transfer because, again, we did no domain randomization, no sys-ID, anything like that. For the entirely new task, this one's really hard. We didn't get that good until we got to 1,000 demos. And then for a entirely new embodiment, obviously zero-shot would have been impossible because it wouldn't even have known what the action space is. But with 500 or 1,000 demos, we can learn quite well on that embodiment. And so again, we can compare this to those vision models if we fine-tune our limited RoboCat to these tasks. For the stacking, the vision models do need quite a bit more data, or don't perform as well with the same amount of data. And for the panda, blue and green, since we already got zero shot, this number is different from the number on the previous slide because it's one object set and the other one was average over all the object sets because we weren't able to train the vision models on all the object sets. Small detail, but that explains why that number is different. So we see that, like, again, more robot data makes it easier to train on future robot tasks, which is, again, not a surprising point, but it's good to, like, make sure we are convinced by it. Yeah.
You tried controlling the, like, splits of data that you trained on? Like, for instance, you just, like, had some panda data and not the Sawyer data, and some Sawyer data and not the panda data. It's probably really expensive to do that, but yeah, is there a way to understand what data is relevant, or is all data good? Because it's like so much data sources that
it is unfortunately very expensive to train these.
Is there like a probing method we could use or something? Like, how do we make sense of this data distribution?
Yeah, good question. So we did do experiments on a smaller scale. The problem is that the small scale experiments don't always reflect back in the large scale, in that it feels like the diversity of data helps. And I have a few points on that later. Maybe that will answer your question, not quite. But it's like, yeah, I mean, I would love to run that experiment, but if we get Google to give me all of the compute, then I can try it. So then we wanted to look at this self-improvement idea because, as I mentioned, we want to be able to generate data and put it back in and improve. And we did this in like the dumbest way possible, which is that we just did behavior cloning with hindsight goal conditioning. There are many smarter ways to do that for future work. But what we compare here is, okay, whether self-improvement helps. So we have 100 to 500 demos of each task. Some of them we have 1,000, but I think for these results, we're only going up to 500. That fine-tune the first iteration of the agent, and then we generated data. So in the light gray, we have if we look at all our generated data for that task, what its success rate was. And again, this was a mix of different agents. This was just all the evaluations we were running on our fine-tuned agents. So we have a lower success rate than our best fine-tuning numbers. And then we take that generated data and add the demos and put that into the training set. So the black bar is that success rate of the demo plus the generated data. And then in blue, we have the final RoboCat iteration performance on these tasks. So we can see on some tasks, we're doing better than the data we trained it on. On other tasks, we're doing worse. And this is potentially due to some tasks we see nice positive transfer from the other tasks in the data. And in other tasks, maybe they're too different. Maybe they're not weighted highly enough in the training. So, but overall, it's not too embarrassing. It would be pretty embarrassing if the data we were putting in was 80% and the agent we were getting out was 20% or something. So it seems like we are learning from this data. But what we really need to compare is whether this self-generated data on its own is improving things. So we made a smaller ablation where we take the iteration 1 training data set plus the demonstrated data, the demonstration data, and train a model on that. And then we take the iteration 1 training data set plus the demonstrations plus the self-generated data and train another model on that independently. And then we compare them on the tasks where we generated data. And so we see here that in orange, just adding the demo data to the main training set is much worse than adding the demo data plus the self-generated data to get a generalist that learns all the tasks plus these tasks. So the self-generated data is really adding additional performance to the generalist agent. And I think this is really about diversity of initial conditions and things like that for those tasks. And then we want to see how much more tasks and data improves RoboCat. And so we look at the final RoboCat model from iteration 2, which includes more tasks and the self-generated data, compared to the limited RoboCat from iteration 1. And we're going to compare this on the tasks that we trained iteration 1 on. So iteration 1 should be, in theory, more specialized to those tasks. These are all sim tasks, like it didn't see any all that distracting real-world data. But it turns out that the iteration 2 is actually better on the task that iteration 1 was only trained on. And these differences look quite small, but this is average over these are sometimes like 30 different tasks in each bucket based on the different objects and perceptual variations. And we're always evaluating over 100 episodes. So each bar can be like 3,000 evaluations. So these small differences seem to be pretty consistently coming out. So this was very exciting for me, that the more data and tasks improve performance, even on tasks that you had already seen. And then if we look at how well these do on fine-tuning, this is less surprising. The model trained on more data and tasks that already saw those objects in a different task is much better at fine-tuning towards further use of these objects in new tasks. And then there's still more transfer capabilities to look at. We didn't study this explicitly, but we had the vegetables were only seen by the Sawyer in the real world, and the fruit were only seen by the panda in our data. And then if we have the Sawyer run given a goal of picking up a fruit, it does a reasonable attempt at that. Sometimes it doesn't. Sometimes it does. That's good. There we go. I dropped it. So as a recap, we have RoboCat solve a large set of, some might argue whether these are dexterous or not. We can argue about that over coffee later. A large set of tasks on multiple real embodiments. We're looking at 250 tasks, 4 embodiments. We adapt to unseen environments with a limited set of demos, and we can incorporate these skills back into the back with self-improvement to perform better and keep improving. And we showed one iteration of the cycle, but maybe it could go on forever, which would be fun. And in terms of what next, as I mentioned, our data generation is very boring, and we just do BC. Wouldn't it be nice if it was better so we could add RL? Right now, we're just communicating tasks with images, but language is a very popular way to condition tasks, so we could have language conditioning in there. Our tasks, again, are still quite limited. We have these RGB objects, we have our fruit and vegetables, but there's a lot of more exciting tasks to work on. And then one thing we were quite limited by in this work was the context of the policy. We could only fit in about 4 time steps based on number of tokens. So as the architectures improve, maybe we can get in-context learning in there as well. How am I doing on time? Okay. So I can also do a brief plug for RTX, or OpenX embodiment, or whatever it's called. I was only slightly with this work, but basically, we've collected a large set of open sourced robotics data sets from 21 institutions. These are all available online. We've got lots of embodiments, lots of skills, lots of tasks. And this is all input sourced together. You can download it into as one big chunk. This is all annotated with language instructions, and it contains a lot of different verbs and nouns, whatever people are excited about these days. But excitingly, we show that we can train a single model on all the data. Here, unlike in the RoboCat thing, the action spaces are all aligned. So they're all like 6 DOF, I think, where each dimension has the same meaning. And then you just train a model on all the data jointly. We do this with RT1 architecture and RT2 architecture. This RT1 is open sourced. You can download it now. You can query it. You can fine tune it to do whatever you want it to do. This one is very large, and I don't think you can download it right now. But what's nice is that, again, it shows the similar concept that if you train a model on all the data, you perform better on the individual tasks than if you train a model only on that individual tasks. And I feel like this was not always true before, and now it is. Now we can actually take advantage of really large data and put them all together and get improvements. So these evaluations were also run by our external partners, which means that it can work outside of Google Lab, it can work in your lab, yay. RT2 shows additional like chain of thought reasoning things. There was some concepts that were only present in the bridge data set, like on top of and near, that were not present in the RT1 data that was on that robot. But then when you query that robot with these instructions from the bridge data, it does actually perform the right movements. So we get cross-embodiment transfer. And yeah, so everything is downloadable here. Cool, and I'm happy to take any questions.
Very nice presentation. How it is actually the earlier demonstration always was on tabletop model.
Yeah.
And with vertical grasping, right?
Yeah.
So can it be transferable to 60 pose?
So for the RoboCat, we had 60 demonstrations as well. Like
the same episodes can be transferred? Means the learning which you are making only for tabletop and vertical grasping.
So we had one embodiment that was doing only vertical grasping, and that was on the Sawyer. And on the Panda, we had full 60 pose teleoperation and demonstrations. So we had, and then I guess what is happening here is this agent is just vertical, and
here all are vertical actually.
no, well, so the fruit, this one it has more degrees of freedom.
Okay, so theoretically, if it is tabletop model, I can learn using only, say, 4 degrees of freedom robot. And then if I want to make the embodiment to transfer to 14 degrees of freedom robot, design robot, how the learning episode will change, how it will adapt?
So we don't line them up. The model just outputs, like that's why we have to do fine tuning. It doesn't just, like it can't just do that on its own. But the model will just have to output more actions because it's like agnostic to that. So we fine tune, when we transfer to the 14 DOF agent, we fine tune on data from that 14 DOF agent.
How you do that, fine tune?
So the model.
How you write the episodes, for example?
So they just have a different spec. Those episodes have an action that has 14 dimensions. And if I can get my computer to scroll, so the images get put in here, and the proprioception And then here it has to output 14 action instead of 7. So it's like outputting more words since it's based on a language model.
My last observation is, do you know about OVMM, right? Open Vocabulary Mobile Manipulation? How it fits to that context? That's far more constraint-wise. It can take mobile as well as manipulation, right?
Yeah.
So it's a kind of subset of that. If you compare your framework with that.
Yeah. I haven't worked with it directly. I think this is more about kind of exploring if we take this kind of generic architecture and put a bunch of data in it and see what happens. So at the architecture level, it's making no assumptions about what the environment looks like. And so we're seeing, okay, we have different embodiments, different tasks, and we train on everything together, and we see if that like helps perform new tasks. But it's not, like on its own, it doesn't know anything. All it knows is the data that goes in. So it's not going to be able to like do something entirely new.
Thank you.
Yeah.
Thank you very much for the nice talk. I really like that the method also works with different embodiments. And I would also want to add something to this tabletop, to more like complex scenes. So obviously there's a gap between humans and robots. And J.J. Gibson showed that actually haptic and tactile feedback is really essential for increasing the grasp success rate or the manipulation success rate even further. Have you thought into that direction of incorporating haptic or tactile feedback? Can you comment on that?
I would love to. I think it's, I agree that it's like makes a lot of manipulation tasks a lot easier. Wait, it's not on here. The new embodiment that we have here, this actually has tactile sensors on it, but we haven't like figured out how to use them yet. And I think that's kind of a common problem with trying to use tactile feedback is how do we actually, like what representation should we use for that if we're in learning? And there's also, I guess, a sense of like the more data we put in, since we're in behavioral cloning, the more sensor data we put in, the easier it is for it to like overfit. So sometimes we want to be careful about that. And then also the slower the inference speed. So for example, this one also has like cameras on the wrist, and we wanted to use them, but then it takes too long to compute the next action. But I totally agree, yeah.
Thank you.
Yeah.
Yeah, thanks a lot for the talk. It's great to see these techniques really work in the real world nowadays. I just wanted, what are your thoughts on, let's say, these more monolithic end-to-end kind of models versus a more kind of, let's say, structured approach, right, where you have certain components and you might use a VLM or an LLM for parts of it, and then you might use some other techniques for motion generation also. Like in your experience, do you think, what are the pros and cons of different approaches?
Mm-hmm. Yeah, I think, I mean, like, what was nice about this is that we just didn't think. Like, we could just not make any assumptions. We didn't constrain our data. We just kind of took whatever we had and put it in. But the generalization results are not very exciting. The hope is just that, like, if we can keep generating data, then eventually it will be good. Well, I think the more what was the word you used? Modular, yeah, that stuff, like, you can expect much more generalization from it. I guess I'm kind of in the camp that, like, we should use whatever we have and, like, put that out in the real world and get a bunch more data and, like, have people interact with things, and then we'll see, like, what we need from there. But, yeah.
At that point, like, why would people deploy this in their homes or whatever, right? Like, what's the socioeconomic plan there? You know?
That is not a part of this equation here. No, I think this was a way for us to think about what can we get out of like a really big model. Well, this was not really big, a medium-sized model trained on all our robot data. I don't think we're going to pursue this exact direction for the next step, but it's I do think the general cycle, though, whether what's in the middle doesn't have to be this particular thing, but I think the cycle of getting something that can do something, whether that's a modular approach or whatever, if it can do something, deploy it, get the data, improve, keep learning, is how we're going to be able to scale up our data collection efforts.
What was the time scale for that iteration that y'all experienced?
Yeah, in theory, it can be very short. Like I think it could be like a 2-week kind of, or 3-week kind of time scale in that training the model took 2 weeks. But while it's training the model, you can collect the tele-up data for the fine-tuning. And then fine-tuning takes like an hour. And then you could collect data for a week. And then you could start your next fine-tuning. Or your next big training. We did 1.5 cycles in like 6 months-ish as we were building all the infra at the same time.
Any other questions? Okay, if not, let's thank Coline again.